Hello, I would like to talk about our work at the University of Washington and our collaborators on factory-centric workforce development program for aerospace industry. Before I introduce myself, I was just to mention that this work is the fruit of collaboration between many people, including people from University of Washington and people from Boeing, our collaborators. Um, and the names are listed here. So to introduce myself, my name is Navid Zoberi. I'm an assistant professor at the Material Science Engineering Department at the University of Washington. And the focus of my research is on processing of composite materials, process simulation, and process characterization. And this work is again on the new workforce education development program that we are proposing at the University of Washington. If you look at the syllabus of a typical university level composite course, and I'm saying that as a person who has been teaching this type of course for the last 10, 15 years at different universities, you can see a common trend that there are topics that we usually cover for engineers at the university level. We start by introducing materials, fibers, resin, prepreg. We talk about manufacturing processes, all the way from AFP to autoclave processing, material characterization, of course, defects, process-induced defects, and then heavy emphasis usually on micromechanics and lamination theory. And that's going from fiber matrix to laminar level to the laminate level. Talked about the mechanics of materials. Talked about different failure theories. And if there are times, usually maybe talking about sandwich theory toward the end, some design, some testing. But the focus, as you can see, is introduction and more emphasis on mechanics usually. If you look at the FAA curriculum standards for composite materials, and FAA has created industry curriculum standards for composite materials on three main functional disciplines, and these are manufacturing, structural engineering, and maintenance. And these have been courses that have been offered in different universities, including Wichita State University, where there are three main courses on composite manufacturing technology, safety awareness. This course covers topics such as introduction to raw materials, processing, machining, inspection, bonding, but heavy emphasis on safety. Composite structural engineering technology, CSET, sorry, which focuses on certification of composite aircrafts. This covers topics such as certification, structural substantiation, the building block approach, the main topics that someone has to know to practice structural engineering. And then, of course, composite maintenance technology, CMT, which focuses on maintenance and repair. Many of these, most of the topics that we cover in these courses are available online. They're public domain information. For example, the CSET course, the information will be published in the later publication of CMH 17. But this shows us a really interesting point in terms of, like, you compare what happens at the university level, what happened at the FAA course, or the practice and engineering needs. There are things that are missing at the university level. These are safety awareness. We don't talk about materials qualification, certification, structural substantiation, building block approach, all the things that are important topics for practicing engineer. The question that we had was, how can we define an effective workforce education program within the university environment with all the limitations that we have in the university, such that it can accelerate the acquisition of necessary skills for aerospace industry? The other things that can be improved, perhaps, that the learning experience for current FAA curriculum standards that exist, can we come up with a better way of an improved and enhanced experiential learning method, which is more focused on hands-on experience, case studies, and project-based teaching. And these are the questions that we had at the beginning. So we believe there are four key components to a successful workforce education program. These are fundamental courses, as I discussed, as following the FAA curriculum standards. These are the things that FAA has been working on for years, starting from 2000, that they have sponsored numerous workshops to develop guidance and policies, creating these courses. So we think this has to be one of the main key components of any successful workforce education program. At the University of Washington, we are planning to develop 2 courses based on these 3 courses available by FAA. Case studies. We think it's extremely important to invite subject matter experts, SMEs, to get involved in these courses, to bring in real life experiences and real life case studies discuss it with the students, and enhance the learning experience of the students by exposing the real case studies. Hands-on labs is the other important aspect I believe is quite important for students and engineers to gain experience doing manufacturing, machining, NDI, maintenance, or repair. And the other thing is that experience has shown that like getting students involved in project and project-based teachings are quite effective to convey the message and the lessons learned in the class to the students. So we think this should be one of the main key components of a successful vocational education program. The question is, how can you have all of these components within university environments and have practicing engineers and graduate students and maybe undergraduate students from university get involved in this? So if you look at the fundamental courses, I'm going to go step by step into these four components and how we are planning to do that within a university environment. Of course, again, courses are based on FAA courses. This has been proven to be quite successful. So we don't want to reinvent the wheel. We want to take what exists, maybe improve upon that, but certainly not reinvent the wheel. So here we talk about one course that covers maintenance and manufacturing, and the main topics we think, following again FAA curriculum standards, is basically essential properties of composite materials, manufacturing process to talk about starting from raw materials, following the materials within the factory environment, between raw materials, storage, preparation for cure and solidification, trim and drill, bonding. Talk about maintenance, of course, about teamwork, source documentation, characterization report, repair, regulations, and the topics important for practice engineers. And again, finishing it, which is with what we think is quite important, and that is engineering design for manufacturing and maintenance. What are the design considerations for that? The other course, again, follows CSET course by FAA, and that is composite structural engineering, following normal topic, starting with applications, processing of application materials, but putting a lot of emphasis on design development and structural substantiation. And these are fundamental things that the student needs to know, starting from lamination theory again, analysis method, failure, but also what are the materials deliverables, what are the design values, knockdown factors, talking about bonding and bolted joints. And of course, for substantiation, talking about regulations, certification, the building block approach, large scale testing, and then finishing it with some advanced topic like flutter, crash worthiness, fire safety, and lightning protection. So these are some of the topics that you basically have in the CSET course. Large scale testing, as I mentioned, impact damage, talking about different damage categories, damage category 1 to damage to category 5, crashworthiness, and of course the building block pyramid, which is the basis of substantiation of a composite aircraft. How do we include case studies in these courses? And that's where we come to the topic of subject matter experts. We believe that this is quite important. It's a key component of a successful workforce education program to involve subject matter experts. And these are people with decades of experience in the industry. And there should be a way that we can convey their experience. They can transfer the experience to new engineers, to practicing engineers. So the way we envision this is that the role of SMEs is to bring case studies, use it as discussion points, to encourage students to interact, and also give them lessons such as there's typically no single results, but it's always trades off between, for example, design and economics. We think this is, again, our belief that the most effective way to bring SMEs and engage them with the students is through asynchronous online format. Think about, I'll show you an example in a moment, but think about the discussion board, which is asynchronized, which means that the SMEs can post questions, then the students can get involved, and it goes back and forth between them. First of all, it gives flexibility in terms of location and schedule for SMEs to get involved. It gives flexibility for students to attend an online format for these courses, which brings me to another case, which fundamental courses, we believe, also have to be given in advanced classrooms where students can participate online as well as in person. So I'll show you an example of how SMEs get involved with case studies. This is basically a real example that my friend who's heavily involved in putting together these courses, Charlie Seaton, who's collaborating with us. It is from his past experiences teaching these courses, FA courses, and creating this online format for students to get involved and SMEs to get involved. It is based on Socratic questioning techniques, which means that the SMEs post the questions. In this case, the SMEs is Christos, as you can see in the list, and then the students get involved. They try to answer, and then the SME and instructor try to basically direct the discussion by asking questions. For example, in this case, SME starts with this question that many assume that all materials purchased under given material specifications are the same. Provide your perspective. Justify your answer if that's correct or not correct. And as if you read through this, it's SMEs and then Charlie Seaton, who in this case is the instructor. They direct the question. For example, they said, imagine that there is a supplier like Excel, that they have a new factory. How do you do material qualification for a new factory? And the students initially might say, as you can see here, says, oh, it's the responsibility of the supplier. Someone says, no, it's the responsibility of the OEM. They directed, eventually it comes out that someone suggested, oh, we have to do tests. And then SME is not satisfied, says, what type of test? And once they have gone through all those discussion points, the SME is satisfied and they conclude the discussion. So we believe this type of mini case studies in this type of online format gives flexibility to both SME and students to move away, think, come back, and then direct the discussion. So we come to the next point, which is the hands-on experience, project-based experience. At the University of Washington, we are setting up a unique facility, which is called Advanced Composite Center. It's a center that has been funded by Washington State, University of Washington, and Boeing Company. So one part of this new center is, of course, having focus on research related to composite materials, manufacturing composite materials. But also a big portion of that is how can we develop a platform for a factory-centric workforce education development program within a university environment. So this center is supposed to replicate a small-scale factory within a university. How can we take advantage of that for workforce education? So if you think about what we envision at this point, this small-scale factory would have the typical things that you might have in a factory. So we will have an AFP. So think about the process of how the part might go through a factory. There's AFP processing, which is the material depositions. There's the processing, autoclave processing, co-bonding, co-curing. Could be thermoset or thermoplastic at this point. You will have machining, NDI, repair. So of course, having such a center invites industry to get involved. They bring industrial projects. So there's an interaction of industry with such a center at the university. There is interaction of faculty members and professors like myself to get involved in these centers and bring research projects here. And that creates an opportunity for both students and engineering practice, engineering training, that they will come in, get involved in this industrial project and research project. As they're getting hands-on experience, they're also involved in these projects. So this becomes a very vibrant platform. What are the advantages of such a platform? So couple of folds. First of all, participation in industrial projects gives a unique opportunity for students to basically gain practical experience, real-world problems. We're not now talking about the hypothetical projects that a student might have in a university. These are real-world problems. They will gain real-world experience. Of course, there is the topics related to IP and if it's allowed for a student to get involved or not. So we have to be mindful of all of those issues as well. There is the research projects, and this also again gives practicing engineers to, first of all, both students and practicing engineers, they gain experience in real world problems, but also when they get involved with research projects, they get expertise in topics that they usually don't get in the typical workforce education programs. What are those? It could be specific types of material and process characterization methods. Numerical methods for process simulation and structure simulation, like hands-on proper FE simulation expertise. Advanced analytics and machine learning, with all the talks on advanced analytics, AI, machine learning. This is a new tool that we believe every engineer should at least be exposed to that and have some experience dealing with that. This provides that opportunity. And of course, connect composite technology challenges to research and training. So make that connection, which we believe is quite important to have a vibrant center. This is topics such as detection and characterization of weak bonds, kissing bond, for example, achieving thermal uniformity during curing process, and so on and so forth. So we think this type of centers that provides all of these components, industry gets involved, faculty get involved, students and engineers get involved, is quite successful recipe for a workforce education program. We talk about research, what type of research topic you might have in such a center, such that engineers getting more experience beyond what they usually get on the workforce education courses. Imagine you start with material characterization in a project, then you do process characterization, you do process simulation, you do failure simulation. At the same time as you're doing that, you're gathering all the data, or you might feed data into these activities from the factory data. You go through the building block pyramid and going through all the different tests to characterize the failure and process simulation to validate those. And then, of course, you may end up doing machine learning to optimize the manufacturing process. So this becomes a very nice research approach to cover many of the topics that, again, usually are ignored in current FAA curriculum courses. So this is our proposed workforce education program. There are advanced classrooms, and in the advanced classrooms, students gain experience by going through fundamental courses, again, following established FAA curriculum standards for composite materials. There is online participation in the advanced classroom, so it doesn't need to be in-person participation. There is the subject matter experts and SMEs that they bring in case studies. It's an asynchronized approach. So think about the Canvas approach where there's a discussion board and students and teachers and subject matter experts can post and can interact. In parallel to that, there is a smaller scale factory, and that's where industry and faculty members get involved with both industrial projects and research projects. And this is where the students who got knowledge, who got experience in doing fundamental course and case studies can now gain hands-on experience in the labs in this small-scale factory, and then do group projects, multidisciplinary groups that gives them more exposure how to interact and collaborate with other people with different sets of expertise. And again, finishing this up by talking about the Advanced Composite Center that we are planning to establish. Again, the goal is to do research. Of course, one of the goals is to do research as data-driven methods and machine learning, cost-efficient and thermoplastic manufacturing. But also, the big component of this for us is the workforce education program. We would like to basically leverage our industry partnership at ACC to transform fundamental research into practice, and then feedback successful technology back into education and workforce development. In summary, at the University of Washington, we are setting up a unique factory-centered workforce education program. We believe it has to have 4 main components. It has to have courses, or what we call the fundamental courses, to be given in advanced classroom. These are following FAA curriculum standards for composite materials, and advanced classrooms such that students can get involved online or in person. There is the involvement of SMEs to bring in case studies in an asynchronized format and interact with the students through the Socratic questioning technique. There's a hands-on experience in Advanced Composite Center, and this is students getting to see AFPs, get involved in doing layups or NDI or repair. Of course, participation in research and industrial projects through Advanced Composite Center. So it becomes this enabler, that's Advanced Composite Center, that students can gain both hands-on experience and get involved in projects. I would like to finish my presentation by acknowledging the funding and support from an industry partner, specifically Boeing Company, but also Washington State for supporting the establishment of Advanced Composite Center. Different departments at the University of Washington involved in this, including Material Science and Engineering Department, Mechanical Engineering Department, and Aeronautics and Astronautics Department. Thank you very much.